Hello. So today is the last webinar. And so we've covered all the topics. So just thermal physics today. So hopefully, hopefully you'll find it useful. And yeah, hopefully you enjoyed the year. So let me share my screen. And okay. Right. I'm glad to hear. Glad to hear, Luke. Right, so thermal physics, everything to do with temperature and heat transfers and thermal energy, of course. Right, so for the first thing we're going to talk about is thermal expansion. As you probably know, when you heat something, it becomes bigger, with very few exceptions. Okay, so for example, water, when you heat water within a certain range between 0 and 4 degrees, it actually shrinks. And this is a very important property of water, which allows to probably, this is the reason why life on Earth exists, because the cold water, sorry, the warmer water is denser. So if you think of a lake, the warm water goes to the bottom and doesn't freeze, because if ice were denser than water, ice would sink, the warm water would go to the top, that would freeze as well. So all the lakes would freeze over the winter. And that means life would probably be impossible in lakes. And as a consequence, life probably would be impossible in other parts of the world. Anyways, this is speculation. I'm not a biologist by any means. Okay. But yeah. Okay, so problem 1. Show that the coefficient of area expansion is 2 times alpha, where and the coefficient of volume expansion is 3 times alpha. What does it mean in terms of percentage increase? So let's talk about thermal expansion. Like, what is thermal expansion? Well, let's say you have a rod and shape rod. If you heat that rod, it would get slightly longer. We call this, the original length is L0, and this we call delta L, that's the additional length. And it turns out that if you divide the additional length by L0, it should equal to alpha multiplied by the change in temperature. Okay, where alpha is the coefficient of thermal expansion. That means for every degree Celsius, the increase delta L, you can rearrange that. So you can rearrange that, rearranging delta L is equal to alpha delta T L0. And you can say, ooh, sorry, that's, let me just check where the direction I'm going into. Okay. Change in temperature. Okay, so and then we have delta L is the final length minus the initial length, L0. And this is alpha. And this is the initial temperature. So the final temperature. Oh, no, sorry. We'll leave it like this. Alpha delta T L0. And then the final length is equal to L0 plus alpha delta T L0. Then, so the final length is the initial length multiplied by 1 plus alpha delta T times the change in temperature. That's another formula. So these formulas are equivalent. Do you understand these two equations? Please let me know. Do you understand what they mean? Do you understand what alpha is? So alpha is the fractional increase per degree. So in simple words, if, so example, L is the length of a rod. So let's say you have a ruler. You have a ruler and you heat that ruler, it will become longer. So L0 is the original length of the ruler. Delta L is the change of length. And we know that delta L is the final length minus the initial length. So example, but I want you to get a feeling of what alpha is. If alpha is, let's say, 0.01, which is incredibly unlikely, right? Let's to be truth, unlikely. So it's usually smaller. If alpha is, means that this means when the rod is heated, it becomes 1% longer for each degree Celsius. Okay, so 0.01 is 1%, right? So if you heat it by 1 degree, it will become 1% longer. Okay. Does that make sense? 2. If alpha is 10 to the minus 4, which is a more realistic value, then heating by 1 degree Celsius increases the length by 0.01%, which is a more realistic value. So for steel, for example, it's 10 to the minus 5. Yeah. All right. And I forgot the units. K to the minus 1 is per degree Kelvin. Per degree Kelvin. Now we need to show that the area expansion is 2 times alpha. So we're going to do that. So the area expansion. Area expansion. Expansion. If we take, let's say, a square plate. Square plate. And then this is L0, and this is L0. So the area is L0 squared. And now let's say this plate becomes slightly bigger. Okay. This becomes L0 plus delta L. And this becomes L0 plus delta L. So the area becomes L0 plus delta L squared. But if we analyze this expression, so it's L0 plus delta L squared. We open the brackets, that's L0 squared plus 2 L0 delta L plus delta L squared. Geometrically, we can see that, let's change color. This bit is L squared, L0 squared. Now this bit is L0 times delta L, and this bit is L0 times delta L. The area, yeah? So that's where the two L0 delta L come from. It's L0 delta L plus L0 delta L. And this small piece is delta L squared. Basically, what I'm saying is that delta L squared is really, really small. Delta L squared is many times smaller than even L0 delta L. So we can neglect this term. Okay. So the area plus the additional area, delta A, is equal to that. But we know the original area is L0 squared. Therefore, we can deduce that the change in area is 2 L0 delta L. And the additional area, so area divided by the original area is 2 L0 delta L divided by L0 squared. L0 cancels, and we are left with 2 delta L L0, which is, by definition, alpha delta T. We had it here, which is 2 times alpha delta t. So we started with this expression. Delta L divided by L0 is alpha delta t. That's the original. But we found that delta A over A0 is 2 alpha delta t. That means that the coefficient of thermal expansion for the area is 2 times alpha. So it's double. So the coefficient of area expansion is double the coefficient of linear expansion. What does that mean? Example. If alpha equals 0.0001 per degrees Kelvin, then for each degree, the length increases by 0.01%, but the area increases by 0.02%. So the area, the percentage area increase is always double the volume increase. Okay. Now volume expansion. Volume expansion. Expansion. Once again, we take a cube. Yeah, it is like a scale factor. Exactly. Thank you. 1.01 squared is 1.02. We take a cube with length L0 and it becomes bigger. It becomes a cube with sides L0 plus delta L. Delta L. So we're interested in this value, the change in volume divided by the original volume. Okay, so change in volume is going to be V0 plus, L0 plus delta L, that's the new volume, minus the original volume, which is L0 cubed, and divided by V0, the original volume. If you open these brackets, it's going to be L0 cubed plus 3 L0 delta L, L0 squared delta L, plus 3 L0 delta L squared, plus delta L cubed, minus L0 cubed. L0 cubed cancels, and you divide the whole thing by V0, which is L0 cubed. So delta V over V0 is, so if you divide these, so it's going to be 3 delta L divided by L0. I've cancelled the squared, plus 3 delta L squared divided by L0 squared, plus delta L cubed over L0 cubed. And the thing is that because L0 is a big number, delta L is a very small number, and a very small number squared divided by a very big number squared is a very small number. So this is, we neglect this term, and we neglect this term. It's a very small term, because as we showed before, delta L squared is very small, delta L cubed is even smaller. And therefore, we got this expression, delta V divided by V0 is the increase in volume compared to the original volume divided by the original volume. This is the percentage increase in volume, is 3 times alpha times delta T. And we can carry on that volume if the volume increases by 0.03%, which is quite interesting. All right, so the volume coefficient, the coefficient of volume expansion is 3 times the coefficient of linear expansion. This is very similar to scale factor, volume factor, area factor, and volume factor. Okay. What does it mean in terms of percentage increase? Well, that's what it means. If, so let's sum this up. Linear expansion is delta L divided by L0. So the additional, there's the fractional increase in length. It's a fractional increase. So fractional or percentage increase. If it's percentage increase, if you multiply it by 100%, increase percentage increase in length. And delta L divided by L0 is alpha, delta T is the change in temperature. Second, delta A divided by A0 is the fractional increase in area, which is 2 alpha delta T. And delta volume divided by V0 is 3 alpha delta T. And if length increases by R%, area increases by 2R%, and volume increases by 3R%. Okay. It's applicable. The applications of this consequence are much wider than that's just thermal physics. Okay, so example, if speed increases by 10%, kinetic energy increases by 20%. Well, 21% technically, but well, have you ever thought of that? If you increase the speed by 10%, the kinetic energy increases by 20% or 21%, but roughly 20%. That's because 1.1 squared is 1.21. Okay, problem 2. How much taller is the Eiffel Tower in the summer compared to winter? Assume alpha is 10 to the minus 5 Kelvin. Apologies for the handwriting. Alpha is 10 to the minus 5 Kelvin. Okay, well, It's an engineering problem, and I like purposefully missing out information from the question, which you either have to research or you do a educated guess, right? So the Eiffel Tower, well, I just happen to know that the Eiffel Tower is about 300 meters. It's 1,000 feet, so it's 300 meters, the Eiffel Tower. So the height of the Eiffel Tower that's L0. L0 is 300 meters. It's technically 331, maybe. It changes as we will see. Okay, so it's made of iron. We know that it's made of iron. It's actually painted, but nevertheless, it's made of iron. So, and we know the thermal coefficient for iron. So alpha is 10 to the minus 5 Kelvin. Now, summer compared to winter, that's very vague, but we can look the values up and how there's the temperature of the Eiffel Tower changes. I'm not going to look it up, but you can. No, we don't. It doesn't have to assume anything. It will work regardless. Absolutely. It's all the dimensions increase. We're just talking about one dimension, so it will increase regardless of whether it's a cylinder or it's that shape. No, it's the actual thing. So yeah. Regardless of the volume. I mean, the volume doesn't matter. The increase in, like, even if the Eiffel Tower was a solid cylinder made of iron of 300 meters, it would weigh a lot, a lot more than it is now. Or it was a single length of an iron wire, a very thin wire of length 300 meters, the answer wouldn't change. Broken junk higher than the Eiffel Tower because they have, yes, that's a good one. Yeah, so, and then we just apply the formula. We just need to estimate the winter and summer temperature. So I think the lowest temperature in the winter in Paris would probably be -20. That's the extremest of the extreme. And in summer, because when the sun is out, the metal can easily heat up to about 50 degrees, plus 50 degrees Celsius. Okay, so let's take, so we have the delta L, the change in length, divided by L0, the original length. Okay, it's alpha multiplied by the change in temperature. So there's going to be, so we can work out the increase in length. Delta L is L0 alpha delta T. So that's L0, that's 300 meters, multiplied by 10 to the minus 5, and multiplied by the change in temperature, which is 70 degrees Celsius. 70 degrees Celsius. So that is, this is Celsius to the -1. So Celsius cancels, of course. And we got 300 times 70 times 10 to the power -5, which is 0.21. 0.21 meters, which is 21 centimeters, which is not a small change. Okay. Yeah, so the Eiffel Tower becomes 21 centimeters, 20 meters taller. Now, what is the volume of the tower? Well, for this, you need to know the density and you need to know the mass. I happen to know the mass of the Eiffel Tower, which is about 1,000 tons. It's 1,000 tons, which is 10 to the 6 kilograms. Do they have to cater for this in the lifts? I'm not sure. That's an interesting question. Lifts out of iron. Yeah, then they would expand at the same rate. Yeah, very good. Mass is so the density of iron is 7,800 kilograms per cubic meter. So therefore, we can talk about the volume of the metal used. That's what I meant. The volume of the metal used is mass divided by density. Yeah, so that's 10 to the 6 divided by 7,800, which is 10 to the power 6 divided by 7,800. So that's 128. So it's about 128 cubic meters. I don't know if that sounds a lot, but what's 128 cubic meters? That's a big room. If you imagine your physics classroom, in school, it would probably about 100 cubic meters, right? Because what's 100? Let's say the room is 8 meters long, 3 meters tall, and 6 meters long. 6 meters, and that's a large classroom. 3 by 6 by 8 that's what 144 cubic meters? No? The Eiffel Tower can be melted down and it will fit in your physics classroom. That's cool. All right. Anyways, it's very thin. The metal that is used is very thin. So that's why it's a marvel of engineering, right? But the best thing about the Eiffel Tower is, of course, the writings on the first floor. If you ever go to Paris, this is what to look out for. Names on the Eiffel Tower. Eiffel Tower. Images. Here. Navier. I can't. I don't know to read some of them. Cuvier, Laplace, Dulong. So all the names that you will study in the first 3 years of university are on that tower. So that's really cool. Like they have Foucault, Becquerel. Becquerel, you know Becquerels? Yeah. So if you go there, this is my favorite place in Paris. Honestly, I like to go and just like read all the names I've been studying for 10 years at university. 8. Anyways, the volume is about 100. So the change in volume we already know, V0. is 3 alpha delta t, and therefore the change in volume we can work out it's V0 multiplied by 3 alpha multiplied by delta, the change in temperature, which is 128 cubic meters multiplied by 3 multiplied by what's that, alpha, which is 10 to the minus 5 multiplied by the change in temperature is about 70 degrees. That's what we estimated. So time 128 times 3 times 70 times 10 to the power minus 5. 0.27 cubic meters. That doesn't sound like a lot, but it's actually 0.27 cubic meters. That's about 207. That's not about. That's 270 liters. So if you imagine 270 liters, that's probably about 3 full bathtubs or two full bathtubs of extra volume. Can you imagine? That's the 2 full bathtubs of iron, of molten iron, that's been added to the tower every summer, and then it disappears over the winter. Well, it doesn't disappear; it just shrinks. 270 liters. That's a lot. Have a child's bath, and it's 50 liters. So it's six full child's bathtubs, which is interesting to imagine. Okay. I don't want to do the whole thing for problem 3. It's just I'm just wary of time. I will do it if at the end if we have time, but I'll just talk you through. So you have a round flask with a rubber stopper and a pipe, and it's full of kerosene. If you heat it by 30 degrees, what was the increase of pressure on the bottom? So of course the kerosene pushes on the bottom, and you know that pressure. So the pressure is density times G times H. Now what happens if we heat the kerosene? The kerosene will go up the pipe. So the height will increase and the pressure on the bottom will increase. And all we need to do is to do a calculation. Well, actually, maybe it's not that bad. Okay, so we know alpha is 10 to the minus 3 for kerosene. Now for glass, alpha is much smaller, is about 10 to the minus 6 roughly. And that is why we can neglect the expansion of glass, because if you think about it, if you heat, the bulb will also expand and the kerosene will expand, but the bulb doesn't increase nearly as much. The increase is 1,000 times less than the kerosene inside. And that's why in these problems, we usually neglect the expansion of glass. Expansion of glass can be neglected. It will say in the problem. But I hope you understand what I mean. So we need to calculate the change in volume of the kerosene. It's going to be 3 alpha. And 3 alpha multiplied by change in temperature. So delta V is equal to 3 alpha delta T multiplied by original volume. So it's 3 times 10 to the minus 3 times the temperature change is 30 degrees times the original volume is 2 liters. Well, should we use liters? It's not the best unit of measurement. Let's use cubic centimeters. So that is 2,000 cubic centimeters. 2,000. So 3 times 3, 9 180. Oh, 180 cubic centimeters. That's a massive increase. Did I do something wrong? So 3 times 0.001 times 30 times 2000. No, it's 180 cubic centimeters. So massive increase. Okay, anyways, the cross-sectional the cross-sectional area of the pipe is 2 square centimeters. So 2 square centimeters. And therefore, the change in height, the volume, the extra volume. So we know the volume is 180 and the cross-sectional area is 2. That means the additional height is going to be 90 centimeters. Yeah? Because if you think about it, it's a cylinder, the height is question mark, the area is 2 square centimeters, and the volume is 180 cubic centimeters. Why is it multiplied by 3? I don't know if you recently joined, multiplied by 3 because the volume expansion, the formula for volume expansion is 3 alpha. Yeah, it does. It does follow because it is in 3 dimensions. Yeah, it does increase in 3 dimensions, and that's the reason. But we've shown that this formula is true for volume. For area, it's 2, and for length, it's 1. All right, so that means the additional height is the volume divided by area, which is 180 centimeters cubed, divided by 2 centimeters squared. We cancel and we get 90 centimeters. All right, 90 centimeters. So the additional pressure it's the density multiplied by G multiplied by H, which is 800. Density is 800 800 kilograms per cubic meter. Multiplied by G is 10 newtons per kilogram. Multiplied by H, which is 0.9 meters. So kilograms cancel. Meters cancel, it becomes meters squared. And we get 9 times 800, 7,200 newtons per kilogram. Oh, sorry, newtons per square meter. Am I mistaken? 800 times 10 times 0.9, 7,200. No, I'm not. Which is 7,200 pascals. Okay, so that's the additional pressure of the additional pressure caused by the volume increase. Interesting. So it is like a thermometer if you think about it. You can use that as a thermometer if you scale it. You can. So does everyone know how to make a thermometer out of this? It's either yes or no. There are no other options. Okay. So you take this thing. This is a bulb with a pipe. And you take a Sharpie. Okay. This is not a Sharpie, but it is a Slytherin pen. Take a Sharpie. You need two things. You need a bath with ice and water. Ice plus water. And you need another bath with boiling water. Boiling water. Okay. If it's a mixture of ice plus water, that means it is at 0 degrees Celsius. If the water is boiling, it usually means it is 100 degrees Celsius. But you don't need any measuring instruments. You know that ice plus water is at 0. You know that boiling water is at 100. And you have this bottle with a pipe. Okay, that's all you need. Now you place it in and you wait for the kerosene to drop. So the kerosene will drop. Let's say the kerosene will drop down to here. You take your Sharpie and you draw a line and you say this is 0 degrees. Once you've done that, you take this thing and you put it in the boiling water. The kerosene level will rise. The kerosene level will rise, will rise, will rise, will rise, will rise. And you stop here. When it stops rising, you draw another line using your Sharpie. And you say this is 100 degrees. What you do then is you take a ruler and you split it into 100 divisions. And that's how you make a thermometer. Okay. This is called calibration. But yeah, in this case, it's how to make a thermometer. And you can use anything, right? So thermometers were made a very long time ago. And you can make one at home. Okay. Does everyone know now? Shaka, do you know? Do you understand? Okay, good. Right. And okay, problem 4. A kettle with a 2 kilowatt heater element contains water with a heat capacity of 5,000 joules per Celsius. While the water is heating up from 8 degrees to 88, 150 kilojoules is wasted, surrounding air. Interesting. Well, first of all, you might have heard that the specific heat capacity of water is 4,200. How come the heat capacity is 5,000? Does anyone know? Could be, but also the units are wrong. What's the unit for specific heat capacity? Kilojoule per degree Celsius per kilogram. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin or per Celsius. Yeah, also possible joules per kilogram per Celsius. They're both equivalent because 1 degree Celsius is 1 degree Kelvin. If you're talking about change, it is calibrated. Look, that is true. So heat capacity without the word specific. Heat capacity. So specific means per kilogram. And heat capacity is measured in joules per Kelvin or joules per Celsius, per degree Celsius. So it depends, heat capacity depends on mass. Depends on mass. Heat capacity, so C, small c, specific heat capacity. The heat capacity is usually either large C, a heat capacity, and there is an expression that C is mc. Capital C is heat capacity is mass times specific heat capacity. So just keep that in mind that these are different things. And so it's heat capacity is how much energy you need to heat something. Oh no, it's 1.2 kilograms of water. 1.2 kilograms means 1.2 kilograms. Is it? 1.2 times 4,200. Roughly, yeah, slightly less than 1.2 kilograms. So 5,000 divided by 4,200, 1.19. 1.19. 19 kilograms. Yeah, 1.2 liter, roughly 1.2 liter. Okay. So we know the formula. The heat transferred is Cm delta T, or it could be written as Q equals C delta T, where C is heat capacity and C is specific heat capacity. Okay, so heat capacity, and C is specific. Heat capacity. Okay. Energy needed. I don't remember what they mean by energy release, but let's energy supplied. Let's call it supplied. Energy needed. What we need is Q equals C delta T, which is 5,000 times 80 degrees, because that's the change in temperature, which is 5,000 times 80, 400 kilojoules, 400,000 joules. So the energy supplied must be 550 kilojoules. And the time taken, well, we know that power is energy divided by time. So time taken is energy divided by power. So it's 550,000 divided by 2,000 watts. Joules would give us divided by 2,000 watts, 275 seconds. So time is energy divided by power, like that. Okay, moving on. Problem 5. Specific heat capacity of copper is 380 joules per kilogram per Celsius. Calculate the heat capacity of a 15 kilogram block of copper. Well, it's very straightforward. Can everyone do that? Just type no if you think you don't know how to do this. It's a simple calculation. It's very, very straightforward. Yes or no? It's just a question about understanding what specific heat capacity is and what is heat capacity. So heat capacity is mass times specific heat capacity. Basically, that's it. So just 15 multiplied by 380, which gives us 15 times 380, which is 5,700 joules per Celsius. Okay, so C is 380 joules per Celsius per kilogram. This is per kilogram, and this is the whole thing, whole block. And that's it. That's all it is. So you need 380 joules to heat 1 kilogram of copper by 1 degree Celsius, or you need 5,700 joules to heat the block by 1 degree Celsius. That's it. Okay. We're getting to the interesting parts. Specific heat capacity of sand is 800 joules per kilogram per Celsius. Calculate the energy required to warm 100 kilograms of sand from 10 to 25. It's a straightforward calculation here as well. So we just need to use the formula. The energy supply, the heat is Cm delta T. And that's it. So it's 800 joules per kilogram per Celsius multiplied by the mass, which is 100 kilograms, multiplied by the change in temperature, which is 15 degrees Celsius. You can see kilograms cancel, Celsius cancels, and we're left with the joules. 800 times 15, that is 1,200, 12,000, 22. So it's 1.2 megajoules. That's it. That's about it. Okay, any questions? Any questions here? Okay. And now to slightly more sophisticated energy calculations. A 50 kilogram iron meteor enters the atmosphere at a height of 100 kilometers and speed of 12 kilometers a second. How much energy is converted into heat? How would you approach that? How would you approach this? Find kinetic energy first. That is correct. Yes. What else do you need? MGH, of course. So you have gravitational potential energy because it's high above the ground, plus the kinetic energy, and all that converts into heat, or thermal energy store, as people like to say these days. All right, converts into thermal energy. Thermal. Oh, and then we need to calculate the gravitational potential energy. So it's the mass mgh plus 1/2 mv squared, which is m is 50 times 10 times 100 kilometers. So it's 100,000 plus 1/2 multiplied by m, which is 50 kilograms, multiplied by v, it's 12,000 squared. And that's a big number overall. So it's 550 times 10 times 1,000 plus 0.5 times 50 times 12,000 squared. What? No, that doesn't make any sense. I accidentally multiplied them. Plus. Okay, 1, 2, 3. 1, 2, 3. 1, 2, 3, 6. 3.65. So 3.65 times 10 to the 9 joules. That's a lot of energy. Okay. How much energy converted into heat? What would be the temperature of the meteor if it retained 20% of its thermal energy? Of this thermal energy? Well, first of all, what is the temperature of a meteor in space? Well, we'll assume it's the temperature of space. And the temperature of space, as we know, thanks to Hertzsprung and Russell. No, not Hertzsprung and Russell. What am I saying? Penzias and Wilson, they discovered the cosmic microwave background radiation. So we know that the universe, the average temperature of the universe is approximately minus 270 degrees Celsius. That's the temperature of space. So we assume it's a 50 kilogram meteor that enters the universe, enters the atmosphere at a temperature of minus 270 degrees. And it heats up. As you know, meteors do heat up when they enter the atmosphere. So it's really hot. Because of this conversion of energy. Okay. So we can say that energy total is equal to mc delta t. And but we say it's 20%, so it's only retaining, so 0.2. 0.2 energy total is that. Okay, so 0.2 multiplied by, okay. So if we want the change in temperature is going to be 0.2 multiplied by the total energy divided by the mass times the specific heat capacity. And this is 0.2 multiplied by 3.65 times 10 to the 9 joules divided by the mass, which is 50 kilograms, and C, which is 450 joules per kilogram per Kelvin, well, per Celsius. let's keep it Celsius. It doesn't matter which one you use. Kilograms, kilograms. So it's going to be something really big, times 0.2 divided by 50 divided by 450, which is 32,400 400 degrees Celsius. And I don't think it matters. The starting temperature actually matters. So the final temperature would be about 32,000. Of course, it loses much more energy. I didn't have time to look up the temperature, the maximum temperature of a meteor. I'm assuming 5,000-6,000 degrees, the top temperature for a meteor as it hits the atmosphere. But you can look that up. 32,000, that's a realistic number. Probably. As I said, I didn't look it up. Okay, I will. What is the temperature of a meteor? 3,000 degrees Fahrenheit. That's not a very high temperature. Approximately 2,000. Okay. That's so. I will go with this number. 2,750. Yeah, sounds about right. Okay. In reality. About 2,000 degrees. Yeah, but we're talking about the average temperature. Right. So if that means that it loses much more than 80% of the energy. So it loses way more than 80% of the kinetic and gravitational energy as it goes in. But also it is still moving. So if you think about it, there's a lot of things going on at the same time. It is moving. It is a fireball and it is moving. So you can't just convert all the kinetic energy. So there's lots of stuff going on here. Physics of meteors, quite sophisticated. Anyways, the point is just the point that I was trying to make is that you use kinetic energy, use gravitational energy, use thermal energy. You need to be able to use them interchangeably. Okay. And there's a question in the assignment. There's a question about the waterfall, and you need to convert gravitational energy into thermal. Now, problem 8, the final problem for today. Supercooled water at -10 turns to ice at 0 degrees. Do you know what supercooled water is? Please let me know, yes or no. It's okay not to know. I'm not expecting anyone to know. It's cool if you do. It is water that is liquid below 0 degrees Celsius. Yes. So this is supercooled water. It is cooled below freezing point, below 0. It's not freezing because in order to crystallize, turn to ice, it needs a starting crystal. It needs a center of crystallization, that's what we call it, right? So, yeah. basically to start, it needs a small piece of dust or something that is to start melting. So it's to start freezing. Now they, yeah. Oh no. It's doing that thing again. Sorry, my computer is being very naughty. Doesn't want to play. I'll just basically they add a drop of another liquid. I'm not sure what they're adding. So here's a drop, and the water immediately turns to ice. As you can see, the water turns to ice, turns milky ice, and then they flow. So what's happening? In order to search to freeze something, you need to take energy away from the system, right? You know that. So we have super cooled liquid. That means it's liquid below freezing point. It's being heated up. It's being heated up to 0 degrees. So the first you have water. So you have water at minus 10 degrees Celsius, liquid water. Now it turns to ice. Well, some of it turns to ice. Ice at 0 degrees. And the remaining water will also be at 0 degrees. So some of the water turns to ice. So what happens is, in order to cool liquid water, you need to take away the heat from it. You need to take its heat, and this is effectively the heat taken away from the ice. It's not a good way of saying it, but I hope you understand what I mean. So there's an energy flow from the ice to the water, and as a result, so some of the water turns to ice by giving off the heat that heats the water. Water freezing gives off heat. And this heat is used to heat the water from minus 10 to 0. This heat heats the water from minus 10 to 0. Okay. So assume the mass of water that turns to ice is mi. So the heat removed to make ice is the mass of ice multiplied by the latent heat of Now all the water heats up to 0. Heat needed to heat needed to heat water is the whole mass of water multiplied by specific heat capacity of water and multiplied by the change in temperature. And these have to be equal because energy goes from the ice to the water effectively. And so that means the mass lost by the ice, so energy lost by ice is equal to energy gained by water. So mass of ice multiplied by latent heat is equal to a mass of water multiplied by specific heat of water times change in temperature. So the mass of ice is mass of water multiplied by specific heat times the change in temperature divided by mass of, latent heat, which is 1 kilogram multiplied by 4,200 multiplied by change in temperature, 10 degrees, divided by specific latent heat. So that's that is 330,000. 330,000, which gives us 4,200 times 10 divided by 0.127 kilograms. Nice. 0.127 kilograms. So yeah, that's it. So what you see here, you see on this in this example, it's not all the water. It doesn't become solid ice. It's just some you have ice crystals mixed with water, right? So the whole thing doesn't become like solid. It becomes more like a jelly, or like snow, British snow. You take it and it's like blah, melts very quickly. Okay. And also, this is an overheated liquid. So this is a water which is above boiling point. So it's more than 100 degrees, but it's not boiling. But if you add some sugar, it starts to boil. And it's not doing it again. Start boiling vigorously. That sometimes happens if you heat water in a microwave, and if it's clean water, it can be more than 100 degrees but not boiling. And if you throw some salt in, it goes explodes. So need to be careful. It's very rare that happens, but if you take a very, very clean cup and very, very pure water, like deionized water, this could happen. But it's not a typical situation. Okay. So now we've reached that. I really want to talk to you about one of the harder problems from the assignment. Yeah. Okay.